In this video, we're going to talk about stoichiometry, and we're going to use a model of making s'mores in order to figure out what stoichiometry is. Stoichiometry really tells us the ratio of ingredients we need in a chemical reaction and how much product we can form. So, for example, we have our list of ingredients to make s'mores. In this case, we need 2 graham crackers, 1 marshmallow, and 4 chocolate squares. So our 2 graham crackers plus our 1 marshmallow plus our 4 chocolate squares will give us 1 s'more. So that's our chemical reaction, quote unquote, for our s'mores. So the question is, how many graham crackers do you need to make 8 s'mores? Well, we need 2 graham crackers to make 1 s'more. So if we want 8 s'mores, we would need 16 graham crackers. Now the way we can do this is we are given 8 s'mores. This is our goal. That's our goal, 8 s'mores. And we are converting it into graham crackers. So we're going from s'mores, and this is like over 1, so we want our s'mores unit to cancel out, from s'mores to graham crackers. Now in here, we need our conversion factor. And in stoichiometry, we call this the mole ratio. If you look here, we have 2 graham crackers for every 1 s'more. So that's our conversion factor. 2 graham crackers per 1 s'more. So that would give us 16 graham crackers are necessary in order to make 1 s'more. How many graham crackers? So that's what we're looking for again. Do you need to make enough s'mores to use up 10 squares of chocolate? So in this case, we're starting with our 10 squares of chocolate. If we go back to our reaction, if we have 4 squares of chocolate, we need 2 graham crackers. That's our ratio. So every 4 squares of chocolate is necessary per 2 graham crackers. So if we have 10 squares of chocolate, we know that 4 squares of chocolate, we need 2 graham crackers for each of those s'mores. So if we have 10 squares of chocolate, we're going to need 5 graham crackers. So what this means is we can really make, with our 10 squares of chocolate, 1, 2, 3. If we have 10 squares of chocolate, we know that there are 4 squares of chocolate per every 2 graham crackers in our s'more. So then there's 4 squares of chocolate for another 2 graham crackers. And we're only left with 2 squares of chocolate, so that's going to be half a s'more. So we only need 1 graham cracker to make half a s'more. So now let's apply this to chemistry. In chemistry, just like in a recipe, we have an equation or a recipe. We have our reactants, what we need in order to make something, in order to make our products. These numbers are called the mole ratio. So this tells us that if we have 2 moles of C4H10, we would need 13 moles of O2 in order to react those 2 moles. And these could form 8 moles of carbon dioxide and 10 moles of H2O. So this is just like saying we need 2 graham crackers and 1 marshmallow and 4 pieces of chocolate in order to form 1 s'more. So once we react all of our ingredients, we no longer have our ingredients, we only have our product, our final result. So how many moles of oxygen, so we're trying to find the moles of oxygen, that's our unknown, are necessary to react with 4 moles of C4H10. Well, from here, we know that 2 moles react with 13 moles. So if we start with 4 moles of C4H10, the ratio is that 2 moles of C4H10 can react with 13 moles of O2. Now notice, I need my C4H10 on the bottom so my units cancel out, and I'll be left with what I want. Whatever I want needs to go on top, which is moles of oxygen. So this would equal 36 moles of oxygen, which makes a lot of sense because to go from 2 to 4, I'm doubling my 2. I'm doubling this number. So I would need to double the amount of oxygen that I have in order to fully react. I'm sorry, I miswrote this. It should be 26 moles of O2. There's another way to think about this, and we call this a BCA table, before, change, after. And I think that this is a much clearer way and can help kind of clarify things. So we're making a table, and the way I'm separating this is I'm just separating it by each reactant and each product. So in my first box, that's going to be for C4H10. My second column is for O2, and so on. So in this case, I am starting with 4 moles of C4H10. So if I start before with 4 moles of C4H10, my change is going to be minus 4. I want to lose all of those moles so that afterwards I'm left with 0. So I need to figure out how much oxygen is necessary to react with the 4 moles. Well, we did that calculation right here. We know that there are 26 moles of oxygen. So I'm going to lose 26 moles, and I'll be left with 0. Now the question is, how much of each product will be produced? So there's a few ways to think about this. I'm going to change what I did for my change, and I'm going to say, let's say I lose 2x. The 2 comes from the coefficient, so if it changes by 2 whatever, my oxygen is going to change by minus 13 whatever. I'm calling it C because that's my change. I start with 0 of each of my products because nothing has reacted yet, and I am producing them, so it's going to be positive, a positive change. And so my first change is going to be a positive 8 change, positive 8C, because this is the mole ratio. That 8 comes from the mole ratio, and so that's how it's changing. And my second one will be positive 10C. So I know that 4 minus 2C equals 0. I get that from right here. So 4 minus 2C equals 0. Well, in this case, then 4 would have to equal 2C, so C would equal 2. So my change is 2. So that means that negative 13C would be indeed minus 26, right? 13 times 2 gives us 26. So that's good because 26 minus 26, so 26 minus 26 gives us 0. So I'm going to plug my 2 in for this C. So I will get 0 plus 8 times 2, which is 16 moles of carbon dioxide. And then again, I'll plug in my 2 as C, and I'll get 20 moles of H2O is produced.